Okay, good morning, everybody. My name's James Bullock, and I'm the Dean of the School of Physical Sciences. And I want to thank all of you for joining us this morning as we kick off the school year. If you keep a sharp eye behind me, you will occasionally see maybe some students walking by. It's kind of a quiet alley right by the park, right behind my office, but occasionally you'll see students taking a shortcut to class, and you might see them back there. It's kind of fun for us to have everything going now on campus. A lot of energy out there. This is our first Compelling Conversations of the year, and we're thrilled to be able to bring you three of our real thought leaders in the School of Physical Sciences. Each one of them is dynamic, and they work in an area of broad overlap, which is technological solutions to the climate challenge we're facing right now. And I think in terms of a sense of optimism, you're going to get nothing better than hear from these three today. It's going to be a great time. You may know that Compelling Conversations is a series we've created. It's actually a fairly exclusive opportunity for you to join us here, and we're hoping to actually do some of this in person as cases begin to drop in Orange County. But this is a virtual event this time. Let me just say, if you're compelled by what you're hearing about and you want to help us do this research, please consider giving. One easy way to do that is to text to give. So you can text PSCC to the number 41444, and you'll be directed to how to do that. Really, any amount will help us, because donated funds are very special, because we could sort of begin exploring things that aren't predetermined by a grant. It's seed funding of that kind is particularly valuable. Let me also say that there's a Q&A button down there. If at any time you have a question, please go ahead. Yep, win in person, and we'll definitely stream it when that happens, so we can still do it sort of both ways. Okay, so let's get started. What I'm going to do is introduce everyone quickly, and then I'm going to ask them in their own words to tell us a little bit about themselves and how they got to this point. So first, I'm going to start with Shane Ardo. Shane is an associate professor in the Department of Chemistry, and he also co-directs the Joint Physics Chemistry PhD program called CHAMP. His research includes efforts to harvest water from the atmosphere, to capture carbon from the ocean, to desalinize water, to store energy via hydrogen and other fuel-forming chemistries. He's also worked on next-generation thin-film solar cells and hydrogen fuels from solar energy. Among many honors, he's received the Moore Inaugural Inventor Fellowship from the Gordon and Betty Moore Foundation and the Beale Innovation Award from UCI. His background is pretty interesting. He has a BS in Computing Applied and Pure Mathematics from Townsend University. He has an MS in Nutrition and Food Sciences from the University of Maryland, and he has a PhD in Chemistry and Photophysical Inorganic Chemistry from Johns Hopkins. Interesting with Shane is before he went to grad school, he worked in a number of different kinds of jobs. He was a software engineer, community college instructor, a high school teacher, and a strength and conditioning coach. So if we need some strength and conditioning later, we can also ask him about that. Next, we have Hu-Lin Shin. Hu-Lin is an associate professor in the Department of Physics and Astronomy. His research studies and builds next generation energy storage and conversion devices that will power our portable electronics, vehicles, and our cities in the future. In particular, he focuses on the study of the fundamental failure modes and degradation mechanisms of batteries and fuel cells. He's going like gangbusters. He's received an MRS Early Career Investigator Award and the MSA Burton Medal, all in the last year, in addition to the 2021 Beale Innovation Award in Physical Sciences. He holds a BS in Physics from Peking University in China and a PhD in Physics from Cornell. Finally, last but certainly not least, is Jenny Yang. Jenny Yang is an associate professor in the Department of Chemistry and also a Chancellor's Fellow for UC Irvine. Her research aims to develop efficient and abundant metal catalysts for the production of fuels or feedstock chemicals using renewable energy. She's looking at new ways to produce hydrogen fuels and to capture carbon dioxide to produce more energy-dense carbon fuels, and more generally, electrochemical carbon capture. Among many other things, many other things. She's a major player in an initiative on campus called Solutions That Scale. She holds a BS in chemistry from the University of California, Berkeley, and a PhD in inorganic chemistry from MIT. So with that, I'd like to open it up and stop talking, and we'll hear directly from the panelists now. So as a way of introduction, Shane, let me start with you. Tell us a little bit about how you got to where you are today in your career and researching what you're doing now.
Yeah, James, sounds great. Thanks for having me here. I really appreciate this. It's an awesome opportunity to share the stuff, the amazing things going in the school and across the university at wide. I was shocked when you gave the intro of the other speakers on the panel that they too did not have, prior degrees in nutrition and math. Joking, of course, right? That does paint a picture of my background. And so, when I was all the way back to high school, I was really kind of in these advanced math programs. And so I didn't really know what I wanted to do with my life and figured I'd just stay the course here with math. And I did enjoy it, of course. So like you said, I ended up getting an undergrad degree in math and computers, and I worked for an IT firm after that. And sitting in front of a computer all day was not my thing. Although, of course, I'm now sitting in front of a computer almost all day, but nevertheless, I wanted to interact with people more. And so I had played soccer pretty competitively. I actually tried out for a professional soccer team as well. And so along my path, I decided I wanted to learn more about the nuances of exercise science, physiology, and nutrition. And so just kind of connecting some dots, I ended up getting a master's degree in nutrition. And when I was there, I took an organic chemistry class, a graduate level organic chemistry class. Thank goodness I didn't take it for credit, because I probably would have got an F. But it really invigorated me and got me thinking a little more about chemical sciences. So yeah, luckily I was able to get into a PhD program at Johns Hopkins, where I studied photophysical inorganic chemistry. A couple of things I left out that I think are very important. Along the way, I wanted to definitely increase my ability to influence others and to interact and train others. And so I did try my hand at teaching at a high school in inner city Baltimore, which I loved. It's called City College in Baltimore City. It was a magnet school for the city, and also taught at a local community college outside of Baltimore. And so I knew I wanted to teach. I knew I wanted to educate. This was kind of where my career was going, but I didn't know what I wanted to do. Did I want to teach math or computers or nutrition or what have you? And so what really drew me to this path of electrochemistry and photochemistry was just searching on the internet, just reading as we do today about researchers, maybe like ourselves on the panel, that are doing cutting edge research in energy, the environment, and photosynthesis. And so it was really a connection to Norman Sutin, Harry Gray, Dan Nocera, some of the big names in the field that really got me into this when I sent them a blind email. And so I just want to kind of end with that. Sorry, it's been a long intro here, but right, I mean, just reaching out to people, reaching out to folks. I hope those on the call will reach out to us. They have children and grandchildren and cousins. They should reach out to us. It's never too late to kind of change careers, get into this field, and I'm sure we're all very, happy to help with that. So,
thanks so much, Shane. Jenny, why don't I go to you next? Tell us a little bit about your background. How you got to where you are now, why you're doing what you're doing these days.
Okay, thanks, James. So excited to be here today. So the reason why I got into the area of chemistry that I'm in is because of an undergraduate research program. So when I was at undergraduate at Berkeley, I was accepted to do a summer internship at the National Renewable Energy Lab in Boulder, Colorado. And when I was there, I actually worked on hydrogen storage in the first sort of big push for hydrogen, 20 years ago. And it was just, to me, it was like, wow, I can apply some of the things that I'm learning in school to solve real problems and to try to push the needle on, renewable energy technology and clean energy and carbon neutral solutions. So I went to graduate school at MIT and I worked for Dan Nocera, who Shane mentioned, who's a leader in the area, because I wanted to learn from him. I learned a lot about bio-inspired chemistry and artificial photosynthesis, a way of basically replicating the process of plants to make carbon neutral fuels. And then I went and did my postdoc at the Pacific Northwest National Laboratory, also to get more training in developing catalysts for hydrogen production. I loved working at the National Lab. It was a great team environment. I love team science. I like interdisciplinary science. I also worked at the Joint Center for Artificial Photosynthesis at Caltech after that. But in the end, I ended up at UCI because, like Shane, I wanted to work with students more and to teach also. And it just gave me a really good opportunity to do that. And to be honest, I love the population of undergraduates at UCI. I mean, the first generation college students, just providing them with the same opportunities to do research and to get inspired and to think about solutions for societal problems.
Jenny, thanks so much. Okay, Hulen, same question to you. Tell us a little bit about, why you're doing what you're doing, how you got here, et cetera, et cetera.
Yeah, absolutely. Compared to Shane, Jenny, I guess my history is a little, less adventurous. But nevertheless, so I was trained in physics, and when I was at Cornell into the PhD program. Specifically, I became an electron microscopist, basically using electrons to look at materials at atomic or subatomic scale. So how I really got into energy materials, electrochemistry, is through a collaboration with chemists. For example, Tito Abrunia at Cornell. At that time, we're super into looking at intermetallic metallics, how we can actually improve the durability of these catalysts in the fuel cell applications. That actually transformed me from a pure electron microscopy into a semi-electrochemist or material scientist who actually started thinking about how we can actually develop and design material and apply them in the energy domain. And after that, I became a scientist at Brookhaven National Lab in the electron microscope facility. So in that 5 years, I actually, because I didn't have to teach, it gave me a lot of time to think and actually to collaborate with a lot of chemists, material scientists in the energy domain. In particular, I pick up lithium-ion batteries as a new topic that I'm interested in. And because of that preparation, after I moved to UCI 3 years ago, these two energy applications quickly grew in my group. And without that time to actually really think and think about the things to prepare myself, I wouldn't be able to actually kind of a semi-transform myself from electron microscopy into now someone who can actually start developing energy storage and conversion materials.
Hulen, thanks so much. And now I'm going to sort of open up the conversation a little bit. One thing I did want to mention, though, you put your finger on electrochemistry. I'm not sure that our audience is fully aware of how strong UC Irvine as a campus is in electrochemistry. Not only in the chemistry department as represented here, in the physics department also as represented here. The School of Engineering has a tremendous group in electrochemistry. We probably are unrivaled. I'm going to be so bold as to say, if you look across the campus, electrochemistry is a real strength, and it's actually sort of at the heart of so many technologies right now that I think are going to drive us towards climate solutions. So it's wonderful to have this group here and to sort of speak in that space as well. So let's talk, Hulen, since we were just with you, I'm going to toss it right back and talk a little bit about batteries. Now, you work on batteries. We're hearing a lot of great things about electrification. We've heard announcements from major car companies all over the world towards a fully carbon neutral, perhaps electric fleets within the next couple decades. What are we going to need to do to get there? And then, we've talked about batteries for sort of cars, and we're a little bit more familiar with that. What are the roadblocks there? And what are some other things that right now are not easy to do with batteries that might open up in the future? So I'll bring that back to you, Hulen.
Yeah, absolutely. I'd love to talk about it. So lithium-ion batteries. So one of the problems with storing the energy into these lithium-containing compound is that the energy density is not particularly high. So with existing, the highest energy density lithium-ion battery that go into our electric vehicles is around 250 watt-hour per kilo. So this energy density is about 1/40 of that of a jet fuel, right? So there's a huge gap there, right? So It works pretty well in our light duty cars, but as soon as it transforms into heavy duty application, for example, 18-wheelers, when you really think about our commercial jet flights, then lithium-ion batteries for short, right? So currently we have a 5-year goal to go from 250 watt per kilo to next to 500 watt per kilo. So that's actually making this battery technology that can be used in heavy duty applications. And if we can go from 500 to 700, 800 watt per kilo, we can start thinking about actually using these batteries in commercial jets. So that's the kind of the roadmap, but to really get from 250 to 700, it's still about 10 to 20 years of roadmap. Yeah.
Fantastic. And, I mean, we'll come back to you a little bit more about some of the things you're working on to get us there. I know you've got a lot of ideas and you're doing some really cool stuff. I guess, let me go ahead and ask Jenny. I know that you are personally excited about electrification, but I know also you've looked at sort of creating more energy dense fuels, perhaps out of more green sources of energy. What are your thoughts right now on sort of your role in this space? And more generally, what are the challenges you think that technology can help us overcome over the next couple of decades?
Yeah, so that's exactly what we're thinking about working on, is basically making chemical fuels from sunlight or other renewable sources of energy. So renewable energy sources have an intermittency problem. Sun only shines in the day. It's not windy all the time. Hydroelectric is a seasonal energy source. And so energy storage is just one of the biggest problems in trying to get to all renewables. And there's a space for batteries, and there's also a space for longer term seasonal storage or higher density storage for transportation, as Hulin pointed out, with jets and heavy duty trucking and things like that. And so what we're trying to do is basically find ways to replace the liquid fuels that we now dig out of the ground and then have a large carbon footprint, and replace them with fuels generated using renewable electricity and carbon taken from the air. And so that when it's burned, it's basically a carbon neutral process. And so our focus at our laboratory is basically making catalysts for this process. And I know Shane works on sort of, using the sunlight directly to sort of help these fuel forming reactions. And so we're sort of complementary that way, which is actually why we collaborate.
Great. So Shane, let's hear a little bit from you. I think one thing I'm particularly interested in is, the stuff you're doing is really using those photons directly to try to do interesting things with in a lot of different spaces, and also overcoming this energy storage issue that we're going to face as we try to go to more green sources of energy. So just your perspective on that right now.
Yeah, thanks so much. And the previous two speakers, thanks for throwing me up a softball here. It was a perfect introduction. I mean, in terms of energy density, I don't think you can get better than the single HH bond, right? Storing energy in a hydrogen molecule. The mass of that is very small. The energy is very big. So in terms of energy density, if you can make hydrogen, now volumetrically, it doesn't have a huge energy density. It's a gas, right? You'd have to compress it and store it. But hydrogen is really kind of a dream fuel in that sense for many different applications. But it depends where you get the hydrogen, right? We can get hydrogen today by taking methane and converting it to hydrogen, but typically the byproduct is CO2. So that, a lot of the hydrogen we get, I believe it's over 90%, is still dirty. It's not just the hydrogen, it's where do you get the electrons and protons to make the hydrogen. So a real key in electrification of making fuels is using water as the source of the electrons and the protons to either make your fuel of hydrogen or reducing CO2, as Jenny said, to some liquid type of fuel, and the byproduct just being oxygen, right? That has a clean and, from the fuel reaction, a net zero, CO2 footprint. So that's really our vision, is to drive so-called direct water splitting to generate hydrogen and oxygen. As Jenny indicated, you can do this renewables today, right? Solar panels and electricity in Southern California are competitive with fossil burning electricity in Southern California. So we have efficient solar panels, but as Jenny indicated, right, that these are all intermittent. So we need to find a way to store. So when you take the cost of your solar panel and then you add it to the cost of your device to do water electrolysis or CO2 reduction, that total cost becomes too large. And so thinking about innovative ways to decrease the net cost of the system to use renewables to make these, carbon neutral or negative fuels is really a challenge. And so that's what my group is particularly interested in. And so just very quickly, what are we working on? We're working with little nanoparticles that absorb light and directly drive the water splitting reactions at their surface. The reason we're particularly interested in this is because if you were to draw a scheme of a reactor, a large scale reactor of how this would look, it doesn't look like a commercial electrolyzer today that already costs too much. It doesn't look like a commercial solar panel. The visions for the reactor designs for these that we're involved in working on look a little more like AstroTurf, or even like a floating little pool toy you'd use, right, to float on top of the pool. There's these little like plastic tubes that you'd unroll in the middle of the desert that could be and are projected to be cost competitive with hydrogen from non-renewable sources today. So this is really our pathway that we're particularly interested in, and we spend a lot of time obsessing over all the nuances from basic science all the way up to techno-economics and deployment and everything in between.
I want to give you three a chance to kind of talk to each other, but I do want to follow up with a question for you, Shane. So is the vision there, you're laying out this microturf in the desert, say in California, and then you're creating hydrogen there, and maybe in pipelines you're sending it, rather than sending natural gas along these pipelines, you're pumping hydrogen to users inland towards the coast. Is that the idea?
Yeah, exactly. I mean, so now if we bring the engineers in the room, right, we're in a physical sciences, we bring our engineering colleagues in and we say, hey, here's my cartoon of how this is going to work. They say, wait a minute, your mass balance is all off here. Where are you getting the water from in the middle of the desert? Your photons are coming in. Okay, great. Where's your water? And what are you doing with your product oxygen and your product hydrogen, right? Now, oxygen you can vent. There's very little value for it on Earth on these large scales. We can talk about that more later, maybe. There's plenty of water actually in the air in the middle of the desert to run high efficiency solar driven electrolysis. So I'm actually not too concerned about the water issue either, even though we are in a drought. Even just taking it from the air, there's a way to do that. What are you gonna do with the hydrogen, right? Of course, you've got to pipe it somewhere and transport it. And we have existing piping infrastructure. So that's extremely powerful to piggyback on that. I agree with that. And if we had Jack Brower, or maybe sitting in your office and told you to ask that or something, right? I mean, he's putting hydrogen in natural gas pipes and doing tests on it right now to see what limits you can have in terms of mixing those. He is pushing that forward through the National Fuel Cell Research Center at UC Irvine, really the world leader to my knowledge in doing this. I mean, again, just to reiterate, we've got a really amazing electrochemistry, renewable energy, hydrogen, CO2 reduction, batteries, energy storage, solar, cohort at UC Irvine. It's amazing to be part of it.
Great. Thank you so much, Shane. Do any of you have comments that you want to toss to each other?
Yeah, I want to chime in here a little bit. So just want to get into infrastructure building a little bit. So hydrogen is great, but the one of the problems with hydrogen is actually not compatible with our existing pipelines. So these metals, they have hydrogen embrittlement. So there's a certain limit of how much hydrogen you can put into existing pipelines. So that's actually, the other thing is hydrogen is really difficult to liquefy. And so storing hydrogen is very critical research. A lot of us actually study, how we can actually store them almost into a compact form like solid, and we can release them back, when we need them with little bit of heat, something like that. And there's also a wide portfolio, something like Jenny or both Shane are working on C1, C2, or even longer chain products. And some of them can be transported and stored using existing pipelines. Some of them cannot. There are a lot of closed loop products. For example, one of them is ammonia. And for many of you, liquid ammonia has the highest energy density compared to all fuels that actually exist in rocket use. And one of the Apollo project actually use liquid ammonia as the propellant. And you can actually form ammonia as a closed loop, just like you can do with hydrogen and water. So there are a lot of things that we can explore, with the tools and the knowledge we have.
Yeah, I think Hulin's exactly right that long-term hydrogen does have some problems because it causes metal embrittlement and things into storage containers. But I think another solution for long-term storage is, as Hulin said, is to turn it into liquid fuels. And so we try to develop catalysts that can basically take CO2 back into its liquid fuel form, the sort of kind that you would dig out of the ground. And then you can use that, and it's perfectly compatible with our current infrastructure now. And the biggest problem is trying to get basically fuels that are that complex that we can dig out of the ground from CO2. But even getting to something like butanol can be used in a diesel engine, for example. And so we just have to get a little bit more complex, and then we can start replacing some of the things that we currently dig out with things that are carbon neutral, carbon negative.
I think one of the things that's sort of fascinating to me about this and kind of awe-inspiring is that I do think that the general consensus is, as we move towards what we hope is a net zero economy, we're going to have to really do a sort of all of the above kind of approach. We're going to have to use batteries for lots of things. We'll probably have to use, we'll be using hydrogen. We'll be using everything at our disposal probably to sort of fill in the niches. And right now we don't know. And we're at this kind of fun exploratory stage where we have people just trying incredibly inventive things all over the map. We don't know exactly what it's going to end up with, but the economic opportunity here, at least for some people, is going to be tremendous. I think when you talk about inventing the future, inventing solutions, I think sometimes people are worried that as we make this transition, it's going to be really bad for the economy. I think most of the experts that I've talked to suspect that it's actually going to be the other way around. There's going to be this amazing explosion of opportunity as we're able to explore these more efficient, and interesting sort of more advanced scientific, ideas about how you create and store energy. So we have a question here. I just want to, from Beth, let's see. The title of this talk implies that there's a reason for technological optimism, but given the timeliness of the discussion for development of sustainable energy sources and storage and all the politics and logistics, et cetera, that's going to be required, can we really avoid the worst effects of climate change while these technologies mature? There's a great question for this panel. Let's hear Jenny. I want to hear from you.
I would love to, yes. So Shane talked a little bit about how we currently get hydrogen from methane. And, my view is that we cannot turn off all of our fossil fuel plants tomorrow, right? Because as you pointed out, the technology is not mature. And so one of the big projects in my lab in the last year has been on carbon capture. And so while we're working toward carbon capture from air, right now a lot of our focus is carbon capture from flue gas, which is fossil fuel exhaust. So you may have heard of clean carbon. It kind of has a bad name as being not very clean. And the reason for that, so clean carbon is usually described as a fossil fuel plant that captures its carbon. But the processes that are currently used are like terribly inefficient. I think the estimate is that in order to capture the amount of CO2 from 1 ton of coal, you have to burn another quarter ton of coal. So it's bad. And one of the things that we work in our lab is basically trying to develop more efficient ways. So we use electrochemistry to capture CO2, and we're basically freed from a lot of the thermodynamic minimums that are used in the current thermal cycles, the Carnot limitations. And so we can approach a much higher theoretical efficiency for these processes. So we actually, just this summer, developed a method for electrochemical CO2 capture from simulated flue gas that's about 3 times more efficient than the current methods using electrochemistry. And so I think that's a big focus, right? Because in my mind, it's better to just not release the carbon. It was always better to not release the carbon. But in the absence of that, since we can't turn off all our fossil fuel plants tomorrow, we need to find ways to basically capture and mitigate the damage that they're releasing to the atmosphere. And then on the way there, we're also developing methods for direct air capture, as well as a way to sort of help draw things down. And that is something I think the first plant opened up in Europe just in the last few weeks, but there's a lot of room for improvement in terms of efficiency and cost for these processes.
Right, and I there's a couple things that several thoughts on this. I think that the cause for optimism here is actually pretty profound. You've seen a phase change in the last 5 years in private industry, where almost many of the major corporations are really tangibly working towards goals of climate neutrality. And it's not just the car companies. I mean, we've been talking on this campus with Southern California Gas quite extensively towards them actually moving towards a company they're not doing methane anymore. I mean, they have a vision where they're not using methane anymore in some future sense. And I think a lot of investment funds are really taking this to heart and thinking about things very seriously. But when Jenny was talking about carbon capture, my mind went to the natural sources of carbon capture. And one of the things I think many people realize is that the ocean is a natural carbon sink. In fact, there's much more carbon in the ocean than in the atmosphere. But the oceans are getting full, and it's bad for life in the ocean as it's absorbing all of this carbon. And I know that's something, Shane, that you've thought a lot about. Maybe you could tell us a little bit about what you're doing in the space of sort of thinking about the ocean for carbon capture and why it's bad to have all this carbon in the ocean right now.
Yeah, James. Yeah, for sure. I think it ties in very well to what Jenny was saying, right? I mean, the amount of CO2 that we emit in the atmosphere every year, I believe I think it's like 9 or 10 gigatons or something like that of carbon. Okay, so it's some number. And I think it's about a quarter of that is sequestered currently in the ocean. Another quarter goes to photosynthesis, and the rest kind of remains. So we're in this really interesting dynamic Earth system, right? Of having the ocean there to definitely be a sink for some of this anthropogenic carbon. The problem is, right, as the CO2, based on simple kind of undergraduate chemistry, when the CO2 goes in the water, it reacts with water, and it makes bicarbonate and a proton. Okay, and that proton is acidifying the ocean, as many of us have heard about, right, which is just wreaking havoc on the ecosystem of the ocean. So just for that reason alone, we want to remove the CO2 from the ocean. Now, at the same time, as Jenny was indicating, right, if you can take CO2 out as a point source, there's a lot of opportunities, as her research is proving, to do something with it. And so the ocean is this vast source. Thank goodness it can sink a lot of CO2. But if we can now, as a point source, try to pull as much out as we can from the ocean, we not only undo ocean acidification, but now we can have a concentrated source of CO2 that hopefully Jenny and Hulin can figure something to do with, right? That we can take it out and make a fuel out of it and have a net, negative carbon advantage. And in doing that and taking the CO2 out of the ocean, we now reintroduce the capacity of the ocean to continue to take CO2 out of the air, right? Because it's actually projected if we don't stop putting CO2 in the air, then the ocean is going to kind of fill up a little bit. They're chemistry words for what's happening, but it's fine. It's filling up and it's not going to act as a sink as well. So I think there's a lot of importance in doing this for many reasons.
So I want to chime in a little bit to think about this in a different perspective, unrelated to politics, more science fiction-like. So I had a physics colleague talking to me. Okay, if your energy storage technology becomes so powerful, so cheap, would it be possible for us to actually send a little energy storage device into space? Capture those solar rays that pass by the Earth, and then beam it back when you need it, where you need it. So my immediate response is that, well, it's possible. It's Tesla's idea, right? And however, the thing is, this is a science fiction idea actually in the 80s, before the global warming started to really be a significant thing everyone knows about, right? And at that time in the 70s, Earth was still cold. Agriculture wasn't really keeping up to keep all the population out of poverty, right? So the science fiction at that time is, okay, can you create a second, sun, right, and shining in Siberia of the Soviet Union at that time, and now and immediately after global warming started to happen, it's not something that people think about anymore, right? You don't want the extra energy that passed by Earth, right? So, however, as our civilization grow, we will need more energy for computation, for transportation, for everything, right? However, if we have this greenhouse gas around us, any energy we beam back to the Earth will stay here, or a large fraction will stay here. They will not radiate back to space, right? So I think it's really important for us to create opportunities for our future children, offsprings, that they can sequester carbon the way they want. They can beam energy to Earth wherever they want. So as our civilization grows, that's just giving everyone a different perspective on why we're working on the futuristic technologies that you might think is related to politics, but we're creating opportunities for our future children.
Thanks so much, Hulin.
Can I take it?
Go ahead. Sorry.
No, it's all right. I wanted to just piggyback on this and say, I mean, I completely agree. I think, right, we're trying to have some forethought here into what happens 100 years down the road. And we're also thinking, what do we really envision for 50 years? What do we 2010, tomorrow? And I think that's an important point to underscore. Just as one example, right, if we didn't really start working seriously on developing solar panels till recently, we wouldn't be where we are today. And as I indicated at the beginning of, my intro or something like that, I mean, the cost of electricity from solar in Southern California is competitive with fossil sources of electricity right now. And so we wouldn't be there today unless we started research before that. And we are where we are today. We're enabled by this because of the fundamental research that then led into the applied research that then led into the development of companies that then influenced, political decisions, influenced society, right? Society has to understand and agree that solar panels are an okay thing to have on your roof, right? And so that's all built up over time, and that's where we are today. So I think doing the research we're doing now is really important to push us forward, as well as constantly thinking about having a portfolio of how can we begin to meet the challenges today, while having enough foresight to also realize maybe they're not going to be the we need. And thank you, right? And with this astroturf in the desert, I'm trying to think more future, and I'd even claim hydrogen from solar water splitting is my vision of 50 years from now being widespread. Whereas now I would actually argue that we should be doing more CO2 reduction and putting things in pipeline and running more internal combustion engine type vehicles. So that's my 2 cents at least.
Well, since you mentioned Hulin and the battery work, Hulin, why don't I would love for you to explain to the audience a little bit about, what you've been doing in terms of different materials that are being used in batteries. Can you tell us that story and about why you're excited about the breakthroughs that you've had?
Yeah, so the thing is, the batteries that go into your phone is in the cathode is primarily containing lithium cobalt oxide, and the battery chemistry that go into your electric vehicle is a nickel manganese cobalt oxide. So all of them have in common is this element called cobalt. So cobalt is toxic, it's really expensive, and the most important thing is that it's almost singly sourced from the Republic of Congo. And over there, the problem is that it's a poor country, and there's a human rights issue there, right? They use child labor to actually mine this mineral, right? It's really difficult to change that, given all the civil wars going on there, and it's really difficult to police a country that's far away from us. Right. So what we have been doing is trying to eliminate cobalt from your battery packs, such that we will use an economic force to actually pressurize those countries that use child labor to mine cobalt minerals, to render them obsolete, such that they don't actually need to do that anymore. So basically, my group has. We're able to invent a field chemistry that can eliminate the cobalt completely from the battery pack that can go into your future electric vehicles. And we're really excited about that.
Yeah, it's an inspiring story. And, for me, let me put my dean hat on for a second. I think a lot of times we talk about environmental justice and we think about that important topic. And I think one of the things that often doesn't come to mind is sometimes basic science innovation can alleviate a tremendous amount of pain and suffering in the world. It's not just about regulations. It's not about, not that that doesn't play a role. It's not, but it's not always necessarily government that steps in and as to be an equalizer. Sometimes a great innovative technology can play a really fundamental role as a force for good in the world. And I think if Hu-Lin and his colleagues are successful here, this is just one example of where, and then also, your batteries will get better along the way. So, so we have a question here from Daryl, which I guess is directed at Shane. And then I want to hear a little bit more from Jenny about where her head is. So Daryl is asking Shane, are you worried about habitat damage in the desert if you're putting this AstroTurf out everywhere? Have you thought about that? Have you consulted with people? Like, what are you thinking in that space?
Yeah, I'm worried about everything. I mean, we need to think about all the aspects of not only the techno-economics, which is the engineering of the device, the technical specs, and the economics associated with that, but also the so-called life cycle assessment of getting and mining the materials, as Hu-Lin discussed, to make these devices. Putting them out there. What's the lifespan of the material? What is the product? How do we think about recycling the end product of one of these devices after it's been used? What's the environmental impact? What's the economic, social, right? There are a lot of things that need to be considered, and my team, in collaboration with many others through a Department of Energy grant, are looking at the details of all of these things related to this AstroTurfy idea. And again, I think the reason is the excitement about this idea that it does have a projection to get you hydrogen that would be cost competitive with hydrogen made today by fossil means, which is really a tall tale because it's very inexpensive today. So anyway, so yes is the short answer of my long answer. The other thing to piggyback on Hu-Lin's comments, I think this is kind of a common theme in electrochemical technologies that we're interested in for energy, is that a lot of the materials used are very expensive. They're often precious metal catalysts, for example, used in electrolyzers to take water to hydrogen and oxygen, in fuel cells to then use the hydrogen and oxygen to power your vehicle or something else. For example, again, a lot of the catalysts are precious metals. And so we don't have lots and lots and lots of them. They're quite expensive. And so I think a real active area of research which can make a splash soon is finding earth abundant so-called alternatives that are less expensive, more easily available in the US and other places we have more control over, which could, depends on the technology, but could greatly decrease the cost of even things today. And so I think that's a really important aspect we look into. And when we move to these materials, oftentimes their activity is still good, but it actually turns out their stability, the device longevity suffers. And these are basic science questions that I think a lot of us on the panel are working on.
Jenny, what does that make you think of, just in terms of all the, the portfolio of things that you're working on? I'm wondering what your thoughts are on this.
I think Shane brings up exactly that important point, which is that a lot of the technology that we have right now is really expensive. And a lot of that is because of the materials that we use are really expensive. And so one of the things in our program that we work on is trying to develop catalysts that can do the same types of reactions, but with abundant metals. And we know that this happens because a lot of the reactions that we're trying to do, water splitting, making H2, there are enzymes in nature that do this with abundant metals. Nature, we always say, can't use platinum, can't use iridium, it would die, right? It just can't find enough. They're not abundant enough. Nature uses nickel and iron. They literally use things that are dirt cheap, right? Because they have to. And so a lot of our work that's bio-inspired basically looks to see how enzymes are able to catalyze these reactions, sometimes even better than any synthetic material that we have, and learn their secrets and try to replicate them in synthetic materials. And I actually wanted to make a comment sort of to that end, and also because of the question about sort of optimism. When I think about the future of renewables, I think there's a lot of fear maybe of other countries coming online and sort of upping their standard of living, and then that's just going to make everything worse. And I agree that that's a concern, but my optimism in this is that, in our country, we have this huge fossil fuel infrastructure that a lot of countries right now are trying to replicate. And, my vision of this is, very much like, we went from landlines and then to cell phones. A lot of countries that sort of came online in the last couple decades, they just skipped the landlines. They just went straight to cell phones. Like, why build all that infrastructure? Why build all those lines? We could just go straight to the newest technology and save all that investment. And my optimism is that, if we think about a portfolio of affordable technologies, then countries that are, increasing their standard of living now can sort of go directly to renewables without building all the pipelines and the type of plants and infrastructure that you need for fossil fuels. So I'm hoping, I think it will take some political will and effort to do it, but my vision would be that that's where the transition really starts.
Mm. Oh yeah, that is inspiring. Wu-Lin, we have a question from Reg for you. So he says, you mentioned the enormous scale of improvements in energy density needed from batteries. How close are we to making transformational leaps that might involve sulfur cathodes, silicon anodes, and similar conversion electrode technologies, where basic research seems to be advancing rapidly?
Yeah, both silicon and sulfur has really high specific capacity, meaning they can store a lot of charge. And they're earth abundant. They're relatively cheap. There are a lot of issues involved with these two materials because silicon, when you store lithium in it, expands enormously, almost 20-fold. So that's really where your electrode can actually start to fail, peeling apart, and delaminate from your electrode. And also for the sulfur, the problem there is really, as soon as the lithium react with it, forms polysulfur to dissolve into existing electrolyte. So there are actually a lot of research going into this. For example, rather than using electrolyte, can we use a solid electrolyte that actually stop lithium sulfur polysulfide from dissolving? That's happening. It's still in the research state. Beyond 5-year type of commercialization scale. And for silicon, there's actually tremendous progress in it. So now we're in a stage we can use almost 20% of silicon mixed with graphite. So that actually has already improved the energy density of the existing lithium-ion battery tremendously, and also enables fast charging that the graphite is not good at.
So thanks. And, I think we have a great question from Beth, actually, which I wanted to get to anyway. So this gives an opportunity. But so her question is, do any of these groups, are any of you partnering with private companies to commercialize your technologies? And I'll just leave that open. I think a couple of you are, but I'll. So maybe I know that you're working with BASF at some level. I don't know if you want to start or.
Actually, so so we're working with a lot of like BASF to actually help them to develop their battery technologies. And also actually I'm in the process of discussing with the VC and starting our own company to actually commercialize this no cobalt materials that was developed by my group. And I want to say that in the battery domain, a lot of things can be quickly capitalized and go into manufacturing and actually benefit our society in a very short term.
Yeah, I guess we're not partnering with any industrial companies right now. I guess I probably haven't even spoken on what my group actually mostly thinks about. We actually work a lot in membranes and in separations. That's actually what we focus mostly on. Going all the way back, given my background, I don't have a background in membrane or separations, but why is it going to stop me? So anyway, that's what we work on now. And so we work on membranes, ion exchange membranes for maybe next generation fuel cells and electrolyzers, some interesting light-driven membranes. I won't get into details now. Separators for ion separations, for desalination and other applications, and these membranes for the CO2 capture from the ocean. So Wu-Lin, we should probably talk more about your electrolyte dissolution and things like that as well. You can probably collaborate on some things too. But nevertheless, we have a fair amount of IP that's come out of our research. I've been at Irvine for about 8 years, and we have, I think, about 5 patents on the different membranes we've been working on. So we're beginning to talk to people and think about startup companies A, B, C, and D, but I really enjoy my day job. So I think I'm going to stay put in sitting in the lab mostly, but I'm interested in collaborating with others in terms of startups or companies or things like that.
I think I might be in a similar space as Shane. So we have patented several things that have come out the last few years. And actually, one of the things that ended up being the most promising, we actually did as a basic science question to develop reversible catalysts for CO2 conversion to formate. And one of my friends who from graduate school who started his company and now works at Lockheed Martin in their redox flow battery space, I just showed him, I said, here's some esoteric thing we did because we thought it was cool, wanted to learn some things. And he was like, this is super important. You should patent it and we should talk. And so, as I said, as Shane said, I like my day job, but I'm not opposed if, if the right parties are interested in starting something. But
I should say that, the Beal Applied Innovation Center at UC Irvine has been a really great, I think, opportunity for some of our faculty. Probably all three of you have been involved with them at some level. I know at least Shane and Hulin are Beal Innovation Award winners. Jenny, you might be, and I just don't know. You're the kind of person who would win it. So it's UCI is really trying to develop that ecosystem now in a way that I think is really powerful, and we're expecting more in that direction as the years go by, for sure. I did want to make sure everybody, I think we're getting some pings on the chat. If you do have a question for the panelists, there should be a thing at the bottom of your sort of Zoom screen that's a Q&A opportunity, and just feel free to go in there and type a question, and then we're happy to answer it. So we have about 7 minutes, and maybe I could open it up a little bit to the three of you. I mean, what are you thinking about longer term? What are the challenges that you're, I don't know, maybe worried about? What are opportunities that you're sort of considering just in this broader question of how do we get to where we need to go in terms of net zero and stabilizing the climate?
I guess I'll hop in and say that one of the best things that's happened in the last few years is the Department of Energy sponsors a lot of workshops, and I've attended several of them. And many of them include people from the basic science side, which I consider myself on, all the way to people who are at companies. And what really struck me is not only how much distance there is between the two, but how little conversation that happens between the different parties involved, from all the way from, bringing things up, and how difficult commercialization is. I always felt like if you have something that's clearly better, then you're done. But it's not true. And there's a lot of work involved, to make something successful, even if it's on paper, makes a lot of sense. And so I feel like, I think the one thing that's changed my perspective in the last few years is that, if you asked me 5 years ago, would you ever start a company? I would say no. That's not really something I'm interested in. But now that I see those challenges and how you really have to be involved and really, be in that process, you can't just sort of hand it off and say, I think I'm done. You have to sort of work with it to the end. And I think it's something I appreciate more than I used to.
Yeah, I do think it's important.
Yeah.
Go ahead, Shane. I mean, I just wanted to sort of add that I do think that this desire to sort of take fundamental discoveries and actually get them out into the world, especially when you're working on new energy technologies, where there's some urgency to kind of get them out into use. I do sense a phase change among faculty, really, in that direction, which probably wasn't like this a decade ago. So, Shane, please go ahead.
Yeah, no, I completely agree with what Jenny said as well. I think taking a step back, it really starts with almost like an education reform almost. So like if we're going to have a future, just as an example that all of us on the panel love and hold near and dear to our heart, right, of like electrochemistry and electrifying things. I mean, I think we need to rethink in the United States how we educate related to electrochemistry. And at UC Irvine, we have, James, as you indicated, a huge cohort of electrochemists, and we're getting together to try to do just that here at UC Irvine, right? To have a educational program that maybe teaches differently than others in the United States, how you introduce electrochemistry, and then also realize the breadth of what it means to be an electrochemist, so that there are enough courses offered and there's kind of a clear outline of how a student could do a program in electrochemistry here at UC Irvine and come out with this amazing expertise that spans very basic science things where students want to use the word electrochemical potential a lot. It's one of my favorite words. You know, we can also get up to mass transfer discussions in engineering, and then all the way up to like real device level considerations and things along that nature. And so, I mean, I think education in this scope is very important. And then I guess to add to that too, just to instill in the students what Jenny said, that, you know, understanding not just getting your degree in whatever and checking the boxes of having the classes, but continuously thinking holistically about learning and being a lifelong learner. I mean, I can't tell you the number of classes I wish I could take every quarter, like just things that I want to keep continuing to learn, because I think it's that holistic view, at least decent knowledge that spreads across basic science to applied science and engineering all the way to real industry is extremely important.
Hu-Lin, anything to add?
Yeah, so what I want to say is really to go to the net zero, it will require a concerted effort from all countries, so education, as Shane mentioned, is really important. So that for the next generation to know the science, and that's backing the the potential politics. And a lot of things, as Jenny mentioned, there's so much innovation in the commercial domain, and so much our fundamental knowledge, our fundamental innovation can go into this domain. However, really for that industry to flourish, to grow, it really needs government to play a role, legislature to play a role. There would need government subsidy for these sectors of industry to actually grow and starting playing roles for the carbon neutrality that everyone really wants. I want to just use one example. For example, the reason we're planting a lot of corn and we actually make a lot of alcohol from that is because of government subsidy. And there's so many actually economists that actually study that, how the government influenced this whole corn alcohol business. And that's one industry that's agriculture industry that's regulated so well by government subsidy. So I think that would happen, and it needs to happen for carbon in the future.
That's a great point, Hu-Lin. I mean, I think we really do need to think a bit holistically. And I think our attitude at UCI, especially if you think about what we're doing with solutions at scale, is to really act as a nexus between policymakers and private industry, academics, researchers, and of course, students, this fundamental piece. We hope to do more and more of that. If you are listening to this and you would like to enable more of what you're hearing about, please consider donating. I mean, as I mentioned before, there's a really special place that sort of donated research dollars can allow us to spearhead just out of the box research projects. A lot of times with government funding, you put in a grant and you have to tell them exactly what you're going to do. And therefore you kind of have to know what you're going to do before you start. And that's not really how science always works. Sometimes you just try something, it's not, and you discover something amazing. And it's these kind of donation dollars that allow us to really do that. Even a little bit of funding can spark something. And if you get a result, if you get a hit, then you go for a bigger government grant to really push it over the finish line. And it's that kind of thing we're trying to innovate and do on this campus. So if you want to help us do that, please do. With that, I want to make sure that I thank our guests today. I mean, you are getting a glimpse of, three faculty who are sort of, I don't know if I call them mid-career, junior mid-career. I mean, these are folks in the prime of their research careers, just killing it. And it's just amazing to be in their presence sometimes. I don't even know. So I appreciate you all giving us an hour, because I know that that probably cost you, you each could have written 2.5 papers probably in that hour. So I appreciate it. But anyway, so thanks for everybody who's joined us today. Thanks, Jenny, Shane, and Hulin. It's been a great time, and we'll keep talking. So till next time, everyone.